So last week we already learned about the hash codes. Okay, so what is hash codes? So it is actually about more the theoretical how you can save the data. So the data can be saved in your memory address, and the data can be in the integer cache, and the data can be in the component sum. So those things are related with the storage in your computer. And the hash codes. Okay. So when we create the hash codes, there is a potential about the polynomial accumulation. The polynomial accumulation means if we have particular bit, you know, bit, so this kind of bit represent the storage in the computer. We have 8 bit or we have 16 bit. We have 30 bit. And now the current computers, it has 64 bits. So this represents how many space you can spare for the storage in the memory. So the higher, of course, the better. But when you have a high bits, it means you need to know how the time will consume the computation. So the partition of the bits of the key into a sequence of components of fixed length. If it is 8 bits, then it will have like 8 space. 1, 2, 3, 4, 5, 6, 7, 8, like this one. If it is 16 bit, then it means we have 8 and we have another 8. And so on. So those things we can evaluate based on the polynomial. So the polynomial means we have the a0 plus a1z plus a2z power of 2 plus a3z power of 3 plus a n minus 1 z n minus 1. So this is at the fixed value of z, ignoring the overflow. So it is suitable for strings. For example, when you have z equals to 33, this is just example, it gives the most 6 collision on a set of 50,000 English words. So if you, let's say you need to build a kind of dictionary. So if we need to build a dictionary, so we need to save the keywords. We need to save, for example, the English word in the computer, and then we need to spare how many quotes do we need for those English words. Let's say we need to have 50,000 English words. Then, with the Z equal to 33, then we can save a set of 50,000 English words. This is just a theory. This is just a theory that this polynomial Pz, this polynomial can be evaluated in ON time. And it is based on the Horner's rule. So I will not discuss in detail about the Horner's because it is mathematically expensive. But just to let you know, so the following polynomials are successfully computed. It's from the previous one with the O1. So if we have P0 of Z, then we have only a n minus 1. If we have Piz, then we have a n I minus 1 plus Z Pi minus 1z and so on. So it means Pz equals to the Pn minus 1 Z. So that's why using this definition, we can have the ON. And also when we do with this space code, we can have the compression function. So before we already learned about the compression function. One of the compression function we use division or using module. Okay, y mod n. Mod means modulo or we call it remainder, remainder or number g. So the size of n in the hash table is usually chosen to be a prime. You know prime? Prime number. It is a number that can be divided by 1 and its own number. So we have like we have 2, 3, 5, 7, 11, 13, 17, 19, and so on. Okay. So we got this is prime number. Number that can be divided by 1 and its own number. So the reason has to do with number theory and is beyond the scope of this course. Anyway, the n, you need to choose from this number. Usually, this number will be a better representation for the compression function. And the other is about the function for making the hash that is multiply, add, and divide, or we call it MAD. So we have AY plus B mod N. So A and B are non-negative integers. Non-negative integers, it means if we have A, so if we do the mathematical operation A mod N, it should not equal to 0. A mod N is not equal to 0. If A mod N not equal to 0, then we can do something for this case. Otherwise, every integer will map to the same value. So that's the reason. If we have A mod N equal to 0, then every value will be 1B. Because when we have A multiplied by Y, when A mod N equals to 0, it means it will not affect the result on these integer values. This is the code to represent the hash map. So hash map is it follows the inheritance from the superclass. So the superclass is the map piece. We learned about the map last week. So this map can be represented in the dictionary in Python. So we want to know more how we can leverage the dictionary into the hash map. So in this hash map, we define the cap is the capacity and P. So P is any value that refers to the compression. Okay. So we have the N, the table, it is the capacity multiplied by the, how many do we have? It is 11 multiplied by null. It means we will set up a null value at the first time. And then N equals to 0. And the prime equals to P. So in this case, we use this number as the prime for the division. And then we want to make the scale. Okay, so the scale, yeah, it is for the MAD. The MAD is the multiply, add, and division. And this is also for the MAD. And this is a shifting from 0 to the p minus 1. We can have the hash function like what we already saw before. So the multiplication multiplied by y modulo n. So modulo n, it is the prime number. And then we will divide with the n, which is the length of the table. The other is the same. We want to know the length. We want to get the item. We want to set the item. We want to delete the item, and we want to resize the capacity. So using the hash map, because we have the capacity, so there might be collision. Collision. What is collision? So we can see from this figure, there might be a crash between the numbers. So collisions occur when different elements are mapped to the same result. Different elements. Means if I have this number, okay, this number is only one, and it is fine. We can save it into this index. But if we have two numbers, what happens? If 004 and 004, we want to put into one storage. It means in this table, we need to have another list. So let's say this is the number. Okay. Let's say we have 54. Okay. 54. We have the table size of 13. So we have 0, 1, 2, 3 until 12. So this is the table size of 13. And we want to store 10 items with integer keys. So this is the integer keys. 54, 28, 41, 18, and then 10, 36, 25, 38, 12, and 90. So we want to save this integer into this table. Okay. So the table we have 14 capacity. So this will appear the collision. For example, this one 54. Now let's suppose the compression function is k mod 13. Then 54 mod 13. 54 mod 13. It is 2. Okay. Then I will place the integer value 54 into the index 2. Okay. I will put into the index 2. What happened to 28? 28 mod 13. It is also 2. So the number 28, when we want to put it into the index 2, because the place only have one box, it is colliding, or we call it collision. Because it is collision, so we want to do something with what we call as separate chaining. So this is separate chaining. Separate means taruh. Okay. Then we want to make another chain. The first is 54, and the next is 28, and then the next is 41. In the case of the index 5, okay, we have only, in the case of index 10, we have 2. In the case of index 12, we have 4 that is connected. So the collision or with the separate chaining, we say that let itself in the table point to a linked list of entries that map that. So for every cell, in the cell, there might be a linked list. So when we have a new element, it will be linked to another element, will be linked to another element. So it is a linked list of a particular point. Separate chaining is simple, but requires additional memory outside the table. So we have already this memory. Let's say if the capacity is 13, then we have at least 13. And if we have another list like this one, then we have another n. So the number of memory that we need for this one, we can have like 13 multiplied by n. Or if there's only pointing this one, yeah, maybe if it is not all of them have n, the maximum will be 13 plus n. But if every point have this one, then it means you will do the multiplication 13 multiplied by n, which is the worst case. So this is the simple algorithm to show how the separate chaining works. So we can delegate the operation to a list-based map. I hope you already know what is list. And then map is based on the dictionary. We have the algorithm of get. So we can get the key with the hash code or hash function of a particular key. We want to put into the key k with the value v. Then, first we need to know about the t. The t is, we want to put the k comma v on the array, which is list in the position it's k. This position represent the hash code. So if the t is null, then n equals to n plus 1. So if there is no value at the first time, or if it is a new key, then n will be added by 1. If we want to remove the k, so we want to check the t from a particular a. Then we can just remove the key k. If t is not null, then n we will decrease by 1. So the insertion, when we have a new key, this is the code. And when we want to remove it, this is the code. So this is the chain has map function. So the chain has map, it is a subclass of has map base. So this is the superclass. Okay. So the bucket item. If the bucket is in the self table J, then check whether the packet is available or not. If the packet is known, then show the key error. If not, then return the packet at the position of key or the index key. So we have table and we have bucket. So here, let's say this is the table. Okay, this one is the previous example. Let's say the capacity is 13. And then for each this one, we will have, well, this is bucket. So the bucket will show where is the key. Key is the key that you want to save. The key is the previous one is 54. Yeah. Previous one is 28 and then 41. So this is the key. So if I want to get the item, then I can just call what is the J? J is this position of the array, and the K. K is the K integer value. If I want to set the item, it means, yeah, I need to check whether the table is known. If the table here is known, for example, okay, then I will make a new bucket, a new possible bucket. So the new possible bucket, we will use the table map. If not, yeah, we will check what is the length of the table. So let's say I have a bucket here, and then I want to check how many keys that are available. And then put the V into this table, and then plus one. So if we have another one, then let's do the plus one for this bucket. If you want to delete the item, so if you want to delete the item, yeah, we just call the table first and then go to the bucket and then check which key is located in the bucket. Then we will delete the bucket. The other thing is only the iteration. So we want to check whether the key exists in the bucket. There is another way to deal with the collision. So the collision, when we have collision, the first is separate chaining. It means I just want to make another new chain. The other is linear probing. So in the linear probing means I want to put everything upon addressing the colliding item is placed in the different cell of the table. So I don't need to make a separate chaining. I don't need to make another new bucket. So I just put in the empty cells. Okay. Just put in the different cells. So linear probing means we want to handle the collision by placing the colliding item in the next circularly available table cell. So each table cell is inspected and it will refer to a probe. So we want to probe for every cell. Colliding items lump together, causing future collisions to cause a longer sequence of probes. So it means if it is collide means if it is overlap, then it requires longer of the sequence. Now let's see. I have the it's x, it is the hash code with the function x mod 13. Now I want to insert a key. So 18. The first key 18 mod 13. What is the result? It is 5. Okay. Then we put the 18 into the index 5. Now I have another 41. 41 mod 13. What is the result? It is 2. So I can put 41 in the index 2. 22. 22 mod 13. The result is 9. Okay. And we put 22 in the index 9. Next, 44. 44 mod 13. The result is 5. 5. Oh, we already have 8. So we cannot put in the index 5. We will go to the next empty cell. The next empty cell is in the 6. So we put 44 here. Now let's do more. 59. 59 mod 13. 59 mod 13. What is the result? 7. Okay, next we put 59 in the index 7. Okay, there is no value in the index 7, so we put 59. Now we have 32. 32 mod 13. What is the result? This is 6. Mark. 6, okay. Then we want to put into the 6. But in the position 6, we already have 3. So we go to the next empty cell. Oh, the number 7 already have value. So we go to the next empty cell. Then we put 32 in the next empty cell. Now let's see 31. 31 mod 13. The result is 5. Okay. Then, okay, let's put into the 5. Oh, in the 5, we have 1. So we go to 6. In the 6, we have another value. We go to 7. In the 7, we have another value. Go to 8. In the 8, we have another value. So we go to 9. In the 9, we have another value. So we go to 10, which is empty. And now we put this one in the this list. 73. 73 mod 13. The result is 61. 73 mod 13. Laten we eigenlijk 65. 8. Okay. So we have 8 and then okay. 8 is not empty. Then we go to this one. 9 is not empty. We go here. 9 is not empty. Then we go to 11. And we put 73 here. So we don't need the separate chain. We don't need another bucket. So we just need to find the empty slot. So whenever we do with the linear probing, we can save the value. But the problem is how to search. Let's have the previous one. Let's have the data like this one. But we need to search. We need to find the value. So we need to have an algorithm. So we need to consider a hash table A that use linear probing. Then in order to get the K, or if I want to get the K value, which is the key, we need to start at the cell HK. And then we probe. So probe means we check one by one. Okay? We probe consecutive location until one of the following occurs. So an item with the key K is found, or an empty cell is found, or n cells have been unsuccessfully probed. So the idea is just similar like the for loop, just like the linear search. If you want to find the key, just do from the beginning until the end of the space. Yeah. When we want to update, it means we can do something like insertion and deletion. So the function will be different. So if it is insertion, it means it is a new data. But if it is update, it means I want to delete the existing data and then put a new data. Okay. So we can do update like this one, first delete and then add a new data, or in the update, we can search and put a new data. Okay, so something like this one is also possible. So using the linear probe or the linear probing, we want to handle with the insertion and deletion. So there might be a special object, we call it available. So available means after I delete the element, then I will make it as available. So a new data can be inserted. So the word remove means first we search for the entry, and then let's say the k comma 0 is k comma o. So this object is found in the index k. Then we replace the special item available and we return the element o. Else we return the null value or not valid. If we want to insert, okay, so this is insert. This is to delete. If we want to insert means, yeah, first we need to throw an exception if the table is full. And then we will start from the cell HK. So HK means the function. Function HK, it is from the X mode. In the example is mode 13. So we will start from this one. So we probe consecutive cells until one of the following occurs. If a cell I is found and that is either empty or available, okay, you can put it. If not, then n cells have been unsuccessfully probed. So you can search the empty items or the empty place if until n places you cannot find a place, then at the end, we just save the K, O in the cell. So this is the code to the probe hash map. So the probe hash map, it is based on the hash map phase. So the object means we want to make the space available. So if it is available, then yeah, we want to make sure that table there is no value, or the table after we do the hash map, if we delete some of the parts, we want to make it as available. So we can find the slot. Find the slot means I want to check whether it is still available or not. If it is still available, okay, and if the first available is none, then you can put it here. If not, then you can check whether the table J is available or not. Or else you can check the key. So if the key has been available, then okay, you can just update. Here we still have the bucket. Okay. So the bucket means we just need to find where is the position of the key. So the bucket here, we want to set the value and the key into the empty space. And delete item means we want to remove the item from the hash table. So there's another concept about the double hashing. Mm, I think I need more time to explain this one. So let me just finish the class until this, and then let's continue on Wednesday. Okay, any questions?